Alright, let's take a look at an example here, and it's going to show us investing $12,000 at 9% annually, and they want to find the balance after 5 years, and we're going to look at three situations. One, where we compound things quarterly, second one, where we're compounding things monthly, and a third one, where we're going to compound things continuously. Now, if you look at the formulas that we've got here, remember, anytime it was more than once a year, we switched to these formulas, and as soon as we went with continuously, then we went with our PERT formula. Alright, so let's put in our values over here. The A again is the amount we're going to end with. Our beginning amount was our $12,000. And then we have 1 plus, now remember our rate is a decimal form. And this time, since it's quarterly, that means it's compounded 4 times a year. So over here we would do 4 times, and they want it to be 5 years. So 4 times 5. So let's do a little simplification before heading to the calculator. So we're going to get 12,000. And in here, you can actually save yourself a little work and make the calculator work a little easier if we do a common denominator. So this would be 4 over 4 added to this, and we're actually going to turn it into 4.09 all over 4. And then 4 times 5 is 20. So again, just a little easier, a little less to put in the calculator, and some simple math you can do already. So then, once we put this in the calculator, it's going to come out approximately, and we'll go to the nearest cent since we're talking in terms of money here, comes out to be close to $18,726.11. So we made about $6,700 in 5 years by going with a quarterly compounding. Alright, let's see what happens when we go with a monthly compounding. Same formula, same things to start with here, $12,000. My pen's not playing nice. We're going to stick with 9%. And here's the change. Since monthly, that means there'll be 12 different times that we're going to compound this interest. But that also means it's going to be 12 times 5 instead of 4 times 5 like in the last problem. So let's walk ourselves through the same steps. We'll simplify a little bit before going to the calculator. This time our common denominator is going to be 12. So we'll make 1 into 12 over 12 and add this. So we'll get 12.09 all over 12. And then 12 times 5 is 60. So now this is the part that we would hit up in the calculator. And again, we get an approximation to the nearest cent. And in this case, we end up with this amount. So a little more than $60 increase by going with the monthly compounding compared to the quarterly compounding. All right, let's take a look what happens if we compound things continuously. We're still starting with our $12,000. This time we're multiplying by that natural exponential function. The rate is still going to be 9%. And we're going to multiply that by our time, which is still 5 years. Now here, a little less to simplify. We can just multiply on the exponent, and we're going to get 0.45. And then all we have to do is, again, hit the calculator up to simplify this. So on this one, again, rounding to the nearest penny, it's going to come out to be about $18,819.75. So each time we compound it more often, we end up making a little bit more money each time. So there's an example of how we can use the two types of formulas, starting with our compounding formula and moving on to our continuously compounded formula. The one that we've got here we can also look at as something called exponential growth. Alright, now just like there's exponential growth, it also works the other way, that we have exponential decay. And one form of that we see a lot of used in practice is the idea of half-life. And my pen is still not working here. The idea of half-life, if we have some substance, we can find out how much of it's going away or how long it'll take approximately for half of it to disappear, and then again another half and so on. So one thing that we can do with that is we can figure out how much we had to start with, we can figure out how long it takes for a certain amount to disappear, and we can use all kinds of applications. So one of the ones that we're going to look at here as an example is the element of radium. And radium has a half-life of approximately 1,599 years. Now, again, restating the half-life, that means whatever amount of radium we have after 1,599 years, half of that amount will have decayed. After another 1,599 years, another half of that would decay, and so on and so on and so on. So let's do a problem with this. Now, we're going to define a few things here. We're going to come up with a formula that takes on this form. And we'll do some different work with half-life eventually, but at least for the start, we're going to do a formula that looks like this. N of t equals n sub 0. And some of this is going to look kind of familiar to what you just got done doing. And then we're going to do 1/2. The exponent gets a little nasty here, so I'm going to try to make it fit somewhat nice. The exponent is t divided by t sub 1/2. Now let me quick define everything here. Our n sub t is our ending amount, n sub 0 is our beginning amount, the t is the amount of time elapsed, and the t sub 1/2 would be the half-life of that particular substance. Now we're going to replace a little bit of this, so we're going to go over here and we're just going to say n sub t equals, we're going to assume that we started this amount and simplified some of this work, and we got n sub t equals a starting amount of 25, and then we've got t over 1599. Alright, so again, we're assuming how much we've got to start this problem off with. So here is our situation. One thing that we want to figure out is, if at the beginning we had this amount was our 25 grams, we're going to take this and we want to find out after 2,500 years. How much would be left? So let's start it out here. Our n sub t, or n of t, sorry, would be 25 times 1/2 raised to the 2,500 over 1599. And that's it. Now we let the calculator do the work for us and simplify it. And it's going to get us approximately and again my pen is not cooperating, 8.46. And like I said, we started with 25 grams, so this will also be in terms of grams. So just another use of exponential work. And again, this type would be exponential decay.